Okay, in the last video, we talked about line integrals and how to define them and a line integral for a function. And we said in this video, we want to expand on that and look at line integrals for a vector field. And I will point out, if we were actually doing this seated, this is one of those lectures where I would say one thing and then just kind of stand there and let you people ponder it, because we're going to start by coming up with a definition by way of an application that you probably all understand better than I do from physics. So a lot of times in class, I would actually just kind of go over brief parts of this lecture and then just stand there and let all of you figure it out using what you understand from physics, because it works well. But since I obviously can't do that, for the purposes of this, I'll sketch everything out, but again, I do stress as you're going through this, this should be something that you remember from physics, and I want to say probably physics too. I'm not positive there, but just keep that in mind. It's something you've seen before. We're just kind of thinking about it mathematically to get to something else. So, like I said, we want to somehow find a way to get a line integral for an entire vector field. Or I guess, a line integral along a curve within that vector field, to say it more accurately. So let's see. In physics, you always talk about work at some point. And going all the way back to middle school, you know the basic formula, work equals force times distance. But ultimately, once you get to maybe high school, you start talking about this in terms of vectors. And maybe the first thing you do is you assume that F is constant. And if F is a constant force and it's going in whatever direction you're, say, pushing something, then it's easy. Work is force times distance, easy formula, plug in, and you're done. Even if you want to transition it to a vector, well, then it would just be work is equal to maybe the magnitude of the force vector dotted with the magnitude of the direction vector. Which is, again, straightforward, but from a real world perspective, not all that realistic. I think the next thing you probably do in physics, and we actually do it in the trig that I teach and in other classes, you say, well, what if the force is not constant? Then you have, or maybe actually, no, before you even do that, you probably say, what if the direction of force is not in the direction of travel? I'm pushing a shopping cart, my force is going downwards at an angle, but the shopping cart is going forwards. But we understand that we've actually talked about, when we talked about vectors earlier in the semester, well, then all I really care about is the force that's going parallel to the direction of travel. But that just means I need to find the force that's parallel to this direction. But the way we actually did that earlier in the semester is by way of just creating the projection and then finding that side of the triangle right there. All of you know this. So then ultimately this becomes f d cosine theta. Just using my understanding of the triangle and the vectors. All of you know this. But the problem is, we are still essentially assuming straight line motion. Again, even if I'm pushing the shopping cart in this straight line, and then it's going in that straight line, vectors, triangles help me figure out which component of the force I care about, but that's still always straight line motion. And in the real world, you have some, particle flying through space. It doesn't move in straight lines, it moves along a curve. And how exactly do I find the work done in moving a particle along a curve? Well, if I know how to calculate the work for a straight line, I can just kind of generalize that to approximate the work along a curve. So let's see. Now, we will change to a smooth curve C, and while I could have a constant force moving along some path in space, if we just think about vector fields we talked about earlier, tornadoes, hurricanes, things like that, obviously at different points within, say, the hurricane, the wind force is different. So if I'm moving through that area, the force is variable based off of where I am in that hurricane, which means it actually is better to think about this from a real world perspective with the variable force. So we will change F to a variable force. And yes, obviously, now we're going to have the vector field F. But now then, again, if I just think about it in terms of a hurricane, maybe my winds are going like this, kind of circular. And then essentially, I pick some path within that hurricane, and at different points along the path, I'm going to have different forces, different force vectors acting on my particle, which looks remarkably like stuff we have done throughout the semester. But that means, since I'm going to have a smooth curve R of t, my parametrization, I have my vector field F, then I know at any point F of R of t acts on the particle. It's a terrible F. So now I have a way to calculate the force at any point along the curve within the vector field. Now I just need to find a way to use that to calculate the total work done. But if I just sketch this out, if this is my curve right here, then we understand that maybe I can have a few points. We'll say R of t sub I minus 1. And then maybe over here we'll have the point at the end of R of t sub I. Over here, this is R of t sub I plus 1. And I can calculate the force at any point there along the curve. But if I want to approximate it, well then maybe I just, use this straight line approach right here, because I kind of know how to calculate that. And admittedly, that won't give me the actual work done, the actual force along this right here, but it'll approximate it. And I could do the same thing right here. And then how am I going to make these approximations get better? Clearly, to get the total force, I'll just add up all of these approximations along the curve. And then how am I going to make that approximation better? Well, I'll just make these vectors get closer and closer together, and ultimately I'll get so close that my curve will essentially be a line there. So we understand the concept of how this is going to turn into an integral. I would point out, I need to calculate the force right here, the direction of travel of my particle, how it's getting acted on along the curve. Which means I need something that moves along the curve in the direction of travel of the curve. But we've done that before too. I'll use, say, this point right here now. That's just my tangent vector. And here I'm deliberately drawing the unit tangent because we understand the unit tangent will make sure I'm going in the correct direction, the direction of force, the direction of travel of the particle. The unit tangent will have magnitude 1, so then I can use other factors to say multiply by the unit tangent to put the correct force on that direction right there. Here I just want to use the unit tangent to make sure I'm going in the right direction. And then I can supply the force myself, because the force will be a vector going in the direction of the unit tangent. So now I can approximate my work. Work is equal to the force R of t sub I star dotted with my unit tangent times the magnitude of the derivative. Again, that will make sure I multiply this by this to get the correct force in that direction of the unit tangent. And then I understand these delta ti's are going to shrink as I make these vectors, these points at the endpoints of the vectors get closer and closer together. So I just have a delta ti there for that right there. And now I have a way to write the work. Or at least in this case, that will give me the work from here to here. But if I ultimately want to get the work along the entire curve, what do? Well, I add them all up. But this will definitely be an approximation. So I take the sum from 1 to n of the f of r of t sub I star dotted with the unit tangent of t sub I times r prime of t sub I, the magnitude of r prime, delta ti. But then that's an approximation. How am I going to make it better? I'm going to make these get closer and closer together, which means I'll take the limit as the magnitude of the partition approaches 0, and then ultimately that will become the limit of a Riemann sum, which will become an integral that I can actually work with. So now, to kind of save a little bit of time here, and I actually do stress, more than likely you have seen some form of this in physics. So I'm going to assume at least some of you probably just fast forwarded through all of this. But I like it. But that just means that now I can actually write that work is equal to the integral from a to b of f of r of t dotted with r prime of t dt. And I would point out right here, this r prime of t is replacing this because, again, this is the direction of the derivative, which is this right here, but it has magnitude 1. If I multiply it by the magnitude of the derivative, I'm just going to get a vector in the direction of the derivative with the same magnitude as the derivative, which means I get the derivative. So now I have a nice, simple formula for my work. But I would also point out, and I do stress here, as we've stressed repeatedly throughout the semester, there's different ways to write these things, and understanding the different ways to write them can help you solve the problem and help you to not get confused if you look things up in different places. And in this case, another way we write this is as the integral from a to b of f of r of t dot v of t dt. Because again, we understand another way to say the first derivative is the velocity. So just be aware, especially because, as I said, you may have seen this in physics. Now we're writing it from a mathematical perspective. And different textbooks in different disciplines will write these work formulas in different ways. But wait, there's more. Because, let's see, what color can I use now? We'll go back to the black one. Before, when we talked about the line integrals for functions, once we had a rough integral set up, we also worked with the differential to do some algebraic fun, maybe. And in this case, I want to look at dr. The differential with respect to r, but that's just dr of t dt. But then by definition, that is also v of t dt. And that may not look like much, that we essentially have this, or this, or this, different ways of saying the same thing. But what it means is, over here, I can rewrite this another way as the integral along the curve f dot dr. But now I know dr is equal to this, so I can rewrite this as the integral of f of r of t dot dr dt, using that notation. Or I can write it as the integral from a to b of f of r of t dot v of t dt, using that notation. And again, here we end up with 3 different ways of writing an integral, and this is most definitely a line integral along that curve. And I want to say your book points out in physics, this is how we generally write this line integral. Maybe because it's how you're used to writing work. Work is equal to force, distance. So that's kind of the standard approach in physics. In math, and earlier in this class, we've tended to use more this form or this form here because I knew exactly what that was. So just be aware, all different ways of saying the exact same thing. I would point out though, again, because we have seen this, this is the line integral, but it's a line integral with respect to arc length, just like we did for our functions before. But arc length is parametrized with respect to s. We have r's, we have t's, there's no s's anywhere. But we said before, last section, when talking about our line integrals, that it is independent of reparametrization, which means this is the line integral for arc length parametrization, but I don't have to use the arc length parametrization because it's the same for all parametrizations. In particular, my parametrization with respect to r or with respect to t. So just be aware of that. But wait, there's more. One of the other things we mentioned when talking about line integrals along functions suppose I try to calculate the line integral along C right here. This path from A to B. Then I could just calculate the line integral along C of f dot dr. And I would point out, again, this is how we tend to write the integral out, or at least in physics, that's a shorthand way of writing it. That's generally not how you would solve it. You would solve it by way of doing something in terms of t and using one of the other forms, because we'll have our f, our vector field, we'll have our r, our parametrization, and we can algebraically manipulate those, plug them into the formula with respect to t, and integrate that. But writing out the problem, we tend to write it this way, because this is, or at least in physics, because this is the simple way of writing out the formula. It behooves you to understand, oh, to solve this, I can use one of the other formulas. But I could certainly calculate the line integral along that path using that formula. But for the sake of argument, what if I wanted to have another line integral along this path going backwards? We said last time that when you have these paths, direction matters. So in this case, if this was C going this way, we would say it's negative C going in reverse. And then the line integral for the path negative C will be the negative of that integral. Magnitude-wise, they will be the same. Integral here, integral there. Numerically, magnitude-wise, they will be the same, but opposite in sign, because one is going left to right, the other is going right to left, for lack of a better way of saying it here. Direction matters, so be aware of that. It also does kind of raising a question to ponder for later. What if my path is, say, a circle? What is that going to do to my line integral? Essentially, I'll be starting and ending at the same point, Does that affect my line integral in any way? Well, this is not a circle, but if I essentially start from here and go to there, then turn around and go back, if this is 10, this is negative 10, combine the two to get the total line integral from beginning to end and back, I'll just cancel out what I got and I'll end up getting 0. Is that always true? If I go from A to B and then from B back to A, I'll clearly get 0 according to this. But what if my A and my B are the same, so to speak? If I go from here to here, will I get 0? I mean, and again, this is one of those things where if we were seated in class, I would just kind of write it on the board and let you ponder. So you can pause the video and ponder this. There is a distinction here which is really important that you want to understand. If I start here and go here, then go back, I start and end at the exact same spot, and according to this, I'll end up getting 0. Because maybe I'll get 10 going this way, negative 10 going back, and I'll get 0. If I start here, go around the circle, will I get 0? I start and end at the same spot. Maybe. This does not say starting and ending at the same spot gives me 0. This says if I go from here to here, then turn around and go back, I'll cancel out what I did. I guess from a physics perspective, there'll be a net of 0 work because I move something over there, then I bring it back. So there's a net 0 amount of work done. Here, for this lemma, I would have to start here, go all the way around to here, then if I turned around and changed direction and went back, I would get the negative of what I started with. Which means going all the way around, then turning around and going back will give me 0, but just starting here and going around and ending at the same point does not necessarily give me 0. The integral could give me any value. Only if I go in the reverse direction do I guarantee that I get 0. And understand the difference there, it is important. And if that's still a little bit confusing, pause the video and ponder it. And then wait, because we'll cover it later in this video or the next video. Which is exactly what we would have done in class. Okay, but this leads to an idea. Circulation. We said when we first drew out these vector fields, the same as what we did when we talked about acceleration. There was straight line acceleration, tangential acceleration, and curved acceleration, normal acceleration. And we said with vector fields, it's kind of the same idea based on the ones we looked at. There are some vector fields that are completely circular. There are some vector fields that are completely straight line, and we had terminology for that. And ultimately, a lot of vector fields will be a combination of the two. So now that we understand what a vector field is and some of its properties and ways to figure out what's going on along paths within that vector field, now we want to start classifying my vector fields. And the first thing we want to look at is circulation. And there's mathematical ways to define this, but the easiest way to think about it is, will a paddle wheel circulate? Or will it move? So if I have a vector field and I sketch it out, and if I think about, say, that vector field being the vector field of a fluid and the motion within that fluid, if I then put a paddle wheel into that fluid, I say the vector field has circulation if that paddle wheel would circulate, if it would spin. If the paddle wheel will not spin, then I say the vector field has no circulation. So harkening back to those two basic ones that we had before. One was completely circular. Clearly, if I drop a paddle wheel in there, it will spin. The other one was completely straight line. If I drop a paddle wheel in there, it's just going to sit there. So that's kind of what we're doing here. We're looking at the vector fields that spin and getting an idea of what that means mathematically and how I can use it. So, to look at an example, the one I already mentioned, f equals negative yi plus xj. which we graphed out before, but I'll sketch it right here. We even threw it in Maple. It's just this vector field right here that spins completely in a circle like this. So now I have a vector field. Now I want to drop a paddle wheel in there that will move along a path, essentially. So my path, R of t, is going to be cosine t, sine t, 0. And I want this to be three-dimensional. This is only a two-dimensional picture, so just make my third dimension 0, like we've done in class before. And we'll only do one circle, so t will go from 0 to 2 pi. So now, see if I get circulation. I'm going to look at the integral f dot dr, which by definition we know is the integral from 0 to 2 pi of f of r of t dotted with dr dt. We've already done these in class, and given that this video is going to be really long anyway, I'm not going to take the time to algebraically calculate these different things out because we've done it in class. F of r of t is negative sine t cosine t 0 dr dt is negative sine t cosine t 0 dt. Now, take the dot product. Negative sine times negative sine is sine squared t. Cosine times cosine is cosine squared t. 0 and 0 is just 0 dt, which means I get the integral from 0 to 2 pi. Sine squared plus cosine squared is 1, so it's just 1 dt, which I then integrate and get t from 2 pi to 0, which gives me 2 pi. Which tells me this integral is positive, so that means my paddle wheel will move within this vector field and it will move in a positive direction, which you all know means it goes in a counterclockwise direction. It also means if I flipped my path around, and instead of going this way, I went this way, I would still get circulation, but instead of getting 2 pi, I would get negative 2 pi. Again, what we were saying earlier, it would be the same magnitude of paddle wheel motion, but it would be in the opposite direction, based off of which direction along the path that I go. So now, we kind of get the idea and how to find it, and I would point out, as I've said in class before, there is the physical understanding, circulation, will a paddle wheel move? We assume that with that particular vector field, a paddle wheel should move, and that's exactly what that integral told us. I'm not going to do other examples here. You can do some for fun. I'll give you some for homework. But essentially, that gives me a way to define circulation. The line integral of a vector field f over a parametrized, simple, closed curve C, which we write like this, is called circulation of F around C. And just so we're clear, this little, you have the regular line integral symbol, path integral, whatever you want to call it for C. If it's a closed curve, we just draw a little circle there, meaning a closed curve. We draw the closed curve. But the line integral of a vector field F over a parametrized simple closed curve C, which we write this way, it's the same formula as before. I just say it's a closed curve. It's called the circulation of f around C. And again, if that circulation, if that integral is positive, I say the vector field has circulation. If it's negative, I say it has circulation going in the negative direction. If it's 0, then the vector field has no circulation. Which, again, if you want to check it in your own time to see how this works, do the other vector field that we did before with straight line divergence. That is clearly not circulating. Figure out the line integral of that along a closed curve, and you should get 0. That's what this is saying. But once we have this, we now get that which is important. The fundamental theorem for line integrals. And to hearken back to that which you have done before, when you were in Calc 1, once you got the basic premise of an integral, you had the fundamental theorem of calculus. The same idea here. We're essentially recreating the fundamental theorem of calculus, but now we're doing it for line integrals as opposed to regular integrals like you did before. The one thing we need, which we did earlier in the semester, so I don't need to take a lot of time here, just recall, if I have d of f composed with r, dt of t, that's equal to the gradient of f of r of t dotted with the r dt of t. And we used that earlier in the semester when we were talking about gradients. So we just need that for this theorem over here. And what we say is, I'm going to need a lot of room. Let f be a continuous differentiable function of 3 variables defined on some domain of f, and that's defined on the domain of the vector field f. And let C be a simple, smooth, parametrized curve given by r of t. So all the same conditions that we've had before. T goes from A to B. And the curve, of course, lies entirely in the domain of the vector field f. The value of the line integral of a gradient vector field delta f along C is given by the integral along C of gradient of f dr is equal to f of r of b minus f of r of a. And this should look familiar. That is the fundamental theorem from Calc 1. Now it's just written in terms of a composition of functions, which is why we needed this. I would point out, though, again, we have all these standard conditions. Let f be a continuous differentiable function of 3 variables defined on some domain, and let C be a simple, smooth, parametrized curve given by r of t that lies entirely in the domain of f. The value of the line integral of a gradient vector field along C is given by that formula there. Which means This only works if I have a gradient vector field. And you recall, it's called a gradient vector field. We also call it a conservative vector field. So this only works for conservative or gradient vector fields. But I still don't actually know what a gradient or conservative vector field is, or at least I don't know how to calculate them yet. I understand the concept. A gradient vector field means that my vector field is the gradient of some vector valued function. But I don't actually know for an arbitrary vector field if it's conservative or not. If it is conservative, if I can somehow show that, then I can use this. And what that means is I don't actually have to calculate out all that integration like I did for the other one. I just do f of r of b minus f of r of a, and I'm done. But I can only do that if it's conservative. But with that, we get a couple of other things. If C is simple closed, then R of B equals R of A. If I have a closed curve, then I start and end at the same spot, which means A and B are the same, which then means I'll get f of R of B minus f of R of A, but R of B and R of A are the same, which then tells me, well, that the line integral gradient of f dr along the closed curve is 0, because those two things are equal. If I had a closed piecewise curve, as long as it was closed, this would still hold. If it was a closed piecewise smooth curve, but then the one example we did do with the paddle wheel moving, that was definitely a closed curve. It was just a circle, 0 to 2 pi, so let's go around the circle once. And I integrated at 0 and 2 pi, which is the same point. And that definitely did not give me 0. So what's going on here? And this is kind of what I was mentioning earlier. There are conservative vector fields, gradient vector fields, where if I take the line integral along a closed curve, I get 0 and it's automatic. And we will see why later on. But if I don't have a conservative vector field, then that is clearly not true. And I'm kind of then stuck with, okay, if I can show it's conservative, then I can assume the solution to the integral. I still don't know how to show it's conservative. I guess I could show it's conservative by showing it's the gradient of another function. I still don't know how to do that, but I could maybe come up with an algebraic way to try to solve that. I could look at the solution to the integral. If I get non-zero if it's a closed curve, I guess I could assume it's not conservative. But if I get 0, does that mean it is conservative or not? And essentially from a math perspective, we end up with a lot of different questions. Does this always lead to that? Does this always lead to that? Does this idea go backwards and forwards or only in one direction? And that's kind of what we have to start thinking about now, so we can really classify my vector fields. Okay. Well, maybe another one of those things that here in class, I would erase everything off the board. And then I would kind of stand there and turn around and look at you and say, okay, let's see. If I have a conservative vector field, I know the value of the integral, the line integral, is entirely based on the starting point and the ending point, and the values there. But And again, now I'm drawing the distinction between a conservative vector field along a path and a conservative vector field along a closed path. Assume you have an arbitrary path that is non-closed. According to the fundamental theorem, if it's conservative, I still just need to find the value of the function, blah, 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 at the end point and the starting point, subtract the two, fundamental theorem of calculus, and I'm done. But then, if I have some vector field, and this is my starting point, and this is my ending point, and there's my path, what happens if I use a different path? If it's a conservative vector field, the value of the line integral is entirely based on the value at the starting point and the ending point, which has nothing to do with the path in between those points, which means this is what's called path independence in math speak. It means the value of the line integral of a conservative vector field is independent of path. It does not matter which path I choose, they all give the same value, which means I don't even need to know what that path is. I just need to know the vector field is conservative. Starting point, ending point, done, easy. But again, as kind of works in math as we look at new things, path independence is true of conservative vector fields. Would it be true of vector fields that are non-conservative? Meaning, if I could maybe show that something was path independent, can I just say I showed it's path independent, that means it's conservative? Or are there other vector fields that are non-conservative that are also path independent, and therefore I can't use that because, again, the goal is to find a trick that will let me show that something is conservative. In order to do this, we need a couple of more tricks. We're going to end this video shortly, and if we were in a seated class, this is literally where I would always end this lecture and split it up over 2 days because there's a lot here. So, we need a couple of new definitions. First, we need what's called a path-connected set. I'm not even going to write a definition here. The idea is pretty straightforward in the name. A path-connected set. A set is path-connected if for any 2 points in my domain, in my set, I can connect them with a path. It does not have to be a straight line path. If that's my domain right there, if I have a point here and a point over here, I can connect them with a path. I can do lots of different paths. It doesn't matter, I can always get from A to B. Obviously, the only way this wouldn't work is if my domain was also over here, because then I couldn't get from there to there. So path connected is pretty straightforward. But from that, we get one theorem that we can use, kind of. Let F be a continuous vector field with domain which is open, path connected, if the line integral of F is independent of path on its domain, then F is conservative. And just so we're clear on the notation here, what this means, we mentioned it before, there exists an F such that the vector field f is the gradient of a vector function f. But again, we now get this connection between path-connected sets and conservative vector fields, but let f be a continuous vector field with its domain, which is an open path-connected region. If the line integral of f is independent of path on its domain, then f is conservative. So again, I'm stuck with, I have to do all of this, and if I can somehow show that all of this is true, then I get that I am conservative. And that doesn't really help me very much at all, because I still have to figure out if all of this is true, then I have to show it's path connected. If I assume it's path connected, I have to show that the line integral is independent of path to then say that it's conservative. But frankly, if I'm already solving out the line integral, then I really only care if it was conservative because it let me solve the line integral out easily. But if I have to solve the integral and show it's independent of path to show it's conservative, that's not really helping me. So there is one more definition we need, and it is what's called simply connected. And I've mentioned in class, we use a lot of the simply connected set. We use a lot of the exact same sounding things to mean 43 different things in math. Where did that one go? It's right here. If every simple, closed curve can be shrunk to a point, then the set is simply connected. What that means is, if my domain, my region, my set looks like this, if I pick a point right here, no matter what closed curve I pick, I can condense that down, I can shrink it down, and ultimately it'll just become a point right there. That is simply connected. If I do the exact same thing, but maybe my region looks like this, where I only care about the deformed donut right there, if I pick this point, can I come up with paths that are simple and closed that will shrink to a point? Definitely. But there are also points and paths I can choose that definitely cannot be shrunk down to a point. So this set would not be simply connected. And I would point out, both of these are path connected. I can certainly connect points with paths. But this is not simply connected. This one is path connected and simply connected. This is path connected but not simply connected. Because when I shrink it down, there's always a hole in the center there. There's topological things going on there from a math perspective. The other thing to just kind of ponder and think about, if I have a three-dimensional sphere, that is clearly path connected and simply connected. If I take a point out of there, if I kind of cut a hole in the center, it's still path connected and it's still simply connected. Because if I have my sphere and there's a hole sitting in the center here, even if I have a path going around that hole, I can deform it, say, downwards around the hole and then pull it together. The only way I couldn't do that is if the hole went all the way through my sphere. The other way to visualize that, make this a three-dimensional cylinder with a hole down the middle. Then you'd end up with the exact same three-dimensional problem I have here. I can never get around that hole, it's always there. And there's this idea from a math perspective, the dimension of your region and the dimension of the holes in that region, say a one-dimensional hole or a two-dimensional hole in three-dimensional space does not stop it from being simply connected, because you can go around the hole. But once your three-dimensional object has a three-dimensional hole, then it fails to be simply connected. And again, that is normally where students' eyes start to glaze over after we've gone through all of this in class. and I say, yeah, we're done, think about this for the weekend, and then we'll come back and try to ponder this and put it all together and see if we can actually figure out what makes a vector field conservative, or how to find a conservative vector field algebraically, if nothing else.